We have quite a bit of ground to cover before we can construct a complete linked list. And remember from the previous video, a linked list is a way of representing a sequence of values, whether they be integers or strings or whatever else, with this property that I can add as many things as I want. There's no inherent limit on the size of a linked list. Getting to that point will take a while because we have to talk about things like allocation techniques before we get all the way there. In this video, what I want to talk about is the syntax machinery that we need. Things like creating types. What I want to do is build a prototype, just one list, and then maybe get comfortable with the way that we work with lists. And then we can, in the next videos, we can talk about things like how do we have a list that we can extend to any number of nodes. So what I need is the ability to represent each node of my list. So each node contains an element. We'll just use integers for the time being. An element and directions to the next node. And I should understand directions here means clearly a pointer in C. So I need a type that represents a single node of the list. Then I want to create 3 nodes, and they'll store the values 6, 10, and 17. Wait, not in that order. 10, 6, and 17. I will use a null pointer to indicate when I'm at the last node. When I'm looking at the last node, instead of directions to another node, it will contain a null pointer. That's my signal that the list is over. So I need a type for a node. I need to create variables to store those nodes. But I also need some way of keeping track of where the list begins. I'm using this special little bit of notation I've created here just to indicate that this thing at the beginning that tells us where the list begins, it is not itself a node of the list. It's just a pointer that tells us where is the first node of the list. Traditionally, we use the term the head pointer to refer to this. And that's because traditionally, the first element of the list is known as the head of the list. So that's all terminology that's well before my time. I maybe would argue that if we're changing terminology, if we had the opportunity to change that, calling it the start pointer might help some things. But we'll stick with the traditional term, the head pointer. So what I want to do at first is create a type to represent a single node of my linked list. And so what does the node have to contain? Let's just mock up what we want here. If I have a variable of type node, what does it need to have? Well, it needs to have an int that stores an element or value or something like that. And then it needs, so maybe this contains the number 6. So this is this node here. And then what it needs is, maybe need more space here. It needs some way of telling you where is the next node of the list. So what I want basically is a pointer here. And the question we have to answer is, what does it point to? So if we look at this element, the node that contains the element 6, the node that comes after it contains the element 17. And it also will have a next pointer. And this next pointer, the one on the node 17, will point to nothing. It'll be a null pointer. Okay, but what is the type of this member? So in my node that contains the element 6, my next pointer should point me at the next entire node. I want my next pointer to tell me where is the next complete node that I'm working with. I want it to be a pointer to a node. Wait a minute, does that mean that it has to have type node star? Well, I think it does. I want my next pointer inside of a node to contain a pointer to another node. And there's something inherently sort of recursive about that if you think about it. The node contains directions to another node. And it turns out that that's actually for good reason. There's actually a very deep and profound connection between linked lists and recursion. And we'll get to that in the last video of the sequence. So I need a structure type. Okay, well, let's try creating my usual new style structure type, type def struct, and I want the name of the type I create to be called node, and what does it have to contain? Actually, before I do that, I'm just going to back up a bit. I want to make sure that my code as it currently exists compiles. So I'll walk through what we're going to get through in the video, which is I'm going to make this type, I'm going to make 3 node objects, And then I'm going to do various things to verify that I know how to work with the list. How do I get an element of the list? How do I loop through the elements of the list? I want to, if a linked list is meant to be a replacement for an array that stores a sequence of elements, clearly it's important that I be able to loop through the list just like I would loop through an array. I want to make a modification and then print the list again to prove that the modification worked. Let's try compiling this. And so it does compile because there's no actual code in it. The reason that's significant is because what I'm going to write here, I want to make sure it compiles too. So I'm going to create a structure type, typedef struct. We're going to call my type node. And let's see, it's supposed to contain an int called element. Fair enough. And then, I guess, a pointer to a node. Node star next. And we'll try compiling this. We'll cross our fingers. But unfortunately, we get this problem. Line 13. So as of line 13, the compiler reads my file from top to bottom. On line 13, I'm using the type node star. And the compiler says, I'm sorry, I've got no idea what you're talking about. I mean, as of, let's see if I can do a little mock-up here. If you're the compiler, as of line 13, this is all you know of the world. Well, there's nothing in this program called node. How do I make a pointer to a type that doesn't exist? That's a bit of a tough one. So we actually have an issue here, and if we remember, think back to the lectures on structs, when I talked about how there are two ways of creating a structure type. And I said it's weird that there are two ways of doing this, the old style way and the new style way. But there's a reason that we're going to need to know both. Okay, so let's get rid of this, and we'll try it again. Let's use the old style definition. Remember that if I define a structure this way, and you might want to go back to the structure video about this because, if it bothers you, because there's a lot of other stuff flying around in this video. Remember with the old style structure definition, the type you create, if you do it this way, is called struct node. Every time you want to work with it, you have to call it struct node, not just node. I don't like that. I don't like the idea of the type becoming a second-class citizen. But if we try this, so int element, and then I have to refer to struct node star next. So the type I'm creating is called struct node, so I have to call it struct node star when I make a pointer to it. Okay, let's try saving that and compiling that. And it works. And that's because when the compiler hits line 13, it says, okay, so you want to make a pointer of type struct node. But yeah, I get it, because I know what you mean, because on line 11, you told me what struct node was. Okay, but I don't like the old style structure definition. I think I understand why I need to use it here. Because when you get to line 13, the compiler has to already know what type you're working with. So what do we do to get around that? I actually think we can get the best of both worlds. I just want to be able to create my nodes. So when I create, let's go down here and mock up what I want to do. I want to make 3 nodes. Node 1, node 2, and node 3. Notice how I want to declare them as just type node. I don't want to use type struct node. How do I get around that? Well, I think what I could do is combine a typedef with. So I want to define a new type called node, and I want it to be the equivalent of struct node. So if you think about it, this would actually define a variable called node of type struct node. It's pretty disgusting looking. What I could use is a typedef to turn struct node into a single type node. That would work. And actually, we can do something else. We can actually combine both versions of structure definition into one long, very odd looking declaration. Typedef struct node. And so here what I'm doing is I'm using both an old style and a new style structure definition in one definition. So I am creating a type called struct node, and it contains an element and a pointer to a struct node. Okay. At the same time, I am defining that type to actually just be called node. So I know this is weird, and I know you're probably not happy that it's coming up now when we're talking about linked lists, which are already pretty complicated, but it's something you have to get used to seeing in C code. It's generally the case that among people that prefer the new style structure definition, this is the way you would typically see a linked list node get defined. So it uses both styles at once. It defines a type called struct node so that it can create this pointer, but then it wraps the whole thing up in a type just called node. And so I do actually realize what I've sketched out over here. My nodes are of type node, and they contain an element, so int element, and they contain a pointer to a node object. I guess formally the pointer is a struct node pointer. But because a struct node and a node are the same thing, we can use struct node star and node star interchangeably. Okay, so I have the type, and yes, I can see why this might cause a certain amount of indigestion. Let's just hang in there and see what we can do with the rest of this code. So what I want to do is I would like to now create 3 node objects to refer to the 3 different nodes in this list. And I'm actually going to deliberately not put the nodes in order. I'm going to use the variable node2 to store the first element, the variable node1 to store the second, and the variable node3 to store the third. Okay, Bill, why are you doing that? That's not going to help us with understanding this. The reason I'm doing this is because I want to make it very clear that we don't care about the names of these variables. The only thing we care about inside of a list is the forward-pointing arrows. If I start with my head pointer and I walk forward, I should go through all the elements of the list. I don't care what order I used for these variables. It turns out that as we go forward, we'll discover that the names of the nodes become completely insignificant. So I'm going to deliberately not have the node names work in order. Okay, so I create a node called node1, called node2, called node3. I also want to make a head pointer. So the goal of the head pointer is that if I have the head pointer, I get directions to the very first node in the list. And that means that what I want the head pointer to be is a pointer to a node. Okay, and I'll just leave this blank and we'll come back to it in a minute. Okay, so let's set up the structure that I have here. Okay, so node1.element contains the value 6 because the node is supposed to contain something called element, and node 1, the one in the middle, contains the number 6 as its element. Node 1.next, which is supposed to be a pointer, will contain a pointer to node 3. Okay, so there's node 3. Okay, and then let's see, node 2.element is equal to 10. Node 2.next is equal to a pointer to node 1. And then node 3.element equals 17, and node 3 will be the end of my list. There will be no next element. I will signal this by saying that the next pointer is equal to null. Now it's important that this is a signal that I have to remember. There's no magic behind using null here. I'm just using this as a sentinel. That means later, for example, if I want to loop over my list, I have to remember that when I hit a next pointer that's equal to null, then I have to stop looping over the list. Okay, so finally, what's my head pointer? My head pointer will give me directions to the very first thing in the list, which in this case is node 2. So I'll make a pointer to node 2. And maybe it's obvious by now, pointers are a pretty big deal when we're working with linked lists. And if you do your dimensional analysis, you might notice that node 2 has type node, which means ampersand node 2 has type node star. So we can do the assignment of that to the head pointer. Okay, so the next, I'm going to try compiling this. There we go. And of course, it's complaining about node 1, 2, and 3. It's saying unused variable. Obviously, I am using them, but the compiler does notice that although I put values in them, I never actually use those values, but it otherwise is not giving me any errors, so that's a good sign. Okay, next task. Print out the first and second elements of the list. So the key thing to understand here is, first off, what I have up here is obviously not a scoping diagram. It's a sketch of the linked list, a structural diagram of the linked list. Maybe we'll dispose of this. So the key thing is, if you ever have to work with linked lists, now or in any other course, and I mean seriously, when I work with linked lists myself, like not when I'm teaching, I often have to sketch out diagrams to work out what I need to do. When you work with linked lists, sketch out a diagram of a list with a few nodes, and then if you need to perform an operation, always think about all you should ever have is that head pointer. If you need some other node of the list, you should only be getting to it by starting at the beginning. My analogy from the previous video was, I've taken all the nodes in the list, there could be 3, there could be 3 million, and I've thrown them out to sea. And you're standing on shore with a piece of rope tied to the first node. All you have is that set of directions. So if you need to access anything in the list, you have to start from that head pointer. Now, we'll talk, not so much in this course, but I'll allude at least later on in a different video to the fact that there are linked lists that are a bit more complicated that go in both directions. You can start at the beginning and go forwards, or you can start at the end and work backwards. Those linked lists have something called a tail pointer. But in general, you should assume if you want to work with the elements of a list, you always start from one end. In this case, we'll start from the beginning because that's all we have, the head pointer. So what's the first element? If I want to get the first element, what I want is the number 10. So how do I get that just from the head pointer? Well, let's see. If I start at the head pointer and I follow the head pointer to what it points to, so the head pointer is a pointer to a node. If I follow that arrow, I get to a node object. And then I ask that node, what is your element? Okay, so head arrow element. What's the second element? Okay, the second element would be start at the head pointer, follow the arrow, and then I'm at this node 2, which contains the element 10. I want to ask that node, hey, what comes after you? I want to ask it for its next pointer, and then I want to follow that and get the element from where I end up. So I take the head pointer, I follow it to get to its element, not to its element. I follow the head pointer to get to the first node in the list. I then get the next pointer from that, and I follow it. Notice how the arrow notation for structs does actually make it a bit easier to read here because we are physically following arrows on our diagram as we write each arrow in the chain. And then I get the element from that node. So start at the head pointer, follow an arrow, and then from the node you get to, take the next pointer, follow that, and then get the element from the node you end up at. Okay, so for the first time, let's try running this. And we can see the first element is 10, the second element is 6. All right, so as I said, have a diagram on hand. And also keep in mind, you may have been skeptical about why we need the arrow notation. You might have said, well, hey, isn't the dot good enough? Why can't I just use the dot and the star for everything? So let's talk about that a little bit. Let me configure this. So here's the version with arrows. Suppose that you don't like using the arrow operator. Well, that's fine. If you want to follow the arrow from the head pointer and get the element, you would do this. So start at head, follow an arrow, and then where you end up, get the element. Okay, great. So that's not so bad. You could do that. But what happens here? So, okay, start at head, follow an arrow. The node you end up at, get the next pointer. Okay, take that next pointer and follow it. And at the node you end up at, get me the value. And this is equivalent. I mean, we can do this, and it works. But maybe you can see now why the arrow operator was such a good idea. It's not so much the need for the dot and the star. It's the really weird cone of brackets that you end up with that makes a real mess out of this. So I'll leave this in, but maybe now we can see why I like the arrow operator so much. It makes the process of following pointers that are inside of structs really convenient, and I think it looks really natural. All right, next task. Print out the entire list using a loop. This is a really tough one to get used to. I'm going to outline what I would do here. So, and you might have to come back and try this a few times. It really would help if you watch the video, give yourself some time, and then see if you can write this loop yourself. It's a tough one. And it's the key behind using linked lists. This loop is the heart of what we are really doing this week. So what I want to do is this. I want to start at the beginning of the list, and I want to walk through every single node until I'm done. I, of course, don't know how many nodes there are. There could be 3, there could be 3 million. So what I want to do is have some way of holding my place. Now, in an array, if we were looping over an array, we would use an index variable. We would use an index variable, I don't know, maybe I. And I is equal to 0 or 1 or 2 or 3. And at each step, we're using the variable I to keep track of where we are in the array. But we don't have that option here because there aren't any indices. All there are this tangled mess of arrows. So here's the way I think I should think about this. Down here, I'm going to make another little pointer. So I'm using this little notation, this X in a circle, to represent a pointer to a node. That's because I don't want to use a box and arrow like I would in a scoping diagram because I'm using boxes to represent the nodes themselves. So I'm going to say, I want to walk through my list. At each step, I want to keep track of what node am I currently looking at. So I'm going to have this pointer called current, and it's going to point to one node at a time. So I'll make a pointer called node star current node. And I'm going to set it equal to, well, let's see, if I'm looping over the list, the first thing I want to look at is the first node. So I'm going to set the current pointer to start at a pointer to the first node. And then I ask myself, hey, where do I have a pointer to the first node in this program? Well, it's here. It's the head pointer. So the type of the head pointer is node star, which means I should be allowed to take the head pointer. Notice that there's no stars and ampersands here. I take the head pointer and I assign it to current node. Okay, so at this step, current points to the first node in the list. And let's try writing a loop like we did back in September. Let's see if we can find a way of writing it without using for or while, and just sort of sketch out the steps, and then maybe take what we end up with and then condense it down into an actual loop. Okay, so at each step, here is what I want to do. Print the element in the current node, and then adjust the current node pointer to point at the next node. Okay, so how do I do that? Well, first, printing out the elements shouldn't be so tough. Just like if I'm printing out the elements of an array, I would say, take the current node pointer, follow it, and get the element from there. Okay, so I've printed out the current element. Now I want to position my pointer so that it's ready for the next iteration. I want to do what is basically the incrementation part of the loop. So I have my current pointer. It's pointing to, at this point, the first node. I print out the first node, so I print out, or the first element, the number 10. Now I want to set up my pointer to be ready for the next iteration, which means I want the pointer to now point at my second node. So the question is, how do I get to this from what I had? So current points at this node here. I notice that if I follow the arrow to get to the node itself and ask this node, hey, what comes next? That'll give me a pointer to the next node in the chain. So I want to adjust my current node pointer by setting it to be current node, arrow next. So I follow the arrow to the node that I'm looking at, and then I ask that node, what is the next thing after this? And then I think if I repeat this 3 times, I will have code that iterates over and prints out the elements of my loop. And there it is, 10, 6, 17. Okay, so let's just see what happens if I walk through this before I turn it into a real loop. Okay, so I start with current equal to head. I print out the element 10, and then I say current equals current arrow next. Okay, so in this case, if I follow the arrow and ask what the next pointer is, it's this arrow here, an arrow pointing at this node. So I adjust my variable current to point here. Okay, now we're down here. Print out the element. Okay, so print out 6, and then do the same thing again. Get the next pointer of the node I'm looking at, and set my current node pointer to point to that. Okay, then go around again, print out the value 17, and then do the same thing. So here, the next pointer of this node is a null pointer, which means current now gets set to that null pointer. All right, now the loop would have to end here. So what we have to figure out is first, okay, do we have enough to turn this into a loop? And if we go by our logic in September, which is once you are literally copying and pasting code, you can just turn this into a loop body, then I think we have a loop. Okay, so this is our loop body. All we need now is a condition. I think we have the initialization, start at the first node, and we have a way of making progress, which is that line current node equals current arrow next. So set up, take our current node pointer and adjust it to point to the next node in the chain. But then the question is, how do we know when to keep going versus when to stop? What is our continuation condition? And here's the thing I've just noticed. When I walk through my entire chain, after printing out that last element, I set the current pointer to equal the next pointer of the element of the node that I'm looking at. So this is the node with the 17. When I look at its next pointer, it's equal to null. If I copy that next pointer into current node ends up equaling null. So maybe what I should do as my condition is say, keep going as long as current node is not equal to null. All right, so let's try that loop out. And there it is. It prints out the list in full, and it stops when current node equals null. If it weren't stopping, so just to be clear, let's try making this an infinite loop. Just to make it obvious, if this loop didn't stop where it did, the program would crash. You can see I tried to loop over all the elements and then something went wrong. What was happening there was current node did equal null, and we tried to follow that arrow and get an element. And we know that if we ever try and follow a null pointer, the program is going to crash. So in this case, while current node is not equal to null, that will be our condition. All right, so we're printing out the list. And I'm actually going to recycle this entire snippet of code down here. I want to print out the list twice. I want to make a modification in between. So here, I use the exact same code again. I just don't redeclare my current node variable. One interesting thing you might want to try with the posted version is see if you can turn this thing into a for loop. And it's possible, and it actually looks really interesting. It's a really elegant looking for loop once you get used to it. So I want to print the list out twice, and then in the middle, I want to finish this last task. Okay, so now the list is being printed out twice. What I want to do now is the task is modify the list to remove the element 6. Okay, so here is the element 6. What do I do to make a modification to this so that the list no longer contains the 6? I want it to just be 10 and then 17. What we're getting at here is how do we do that splice operation that linked lists are apparently so famous for? Here is what I think we need to do. If I start here and I walk along, I go 10, then 6, then 17. I observe that if I want the 17 to come directly after the 10, maybe it's as simple as adjusting this pointer here. I mean, sure, the 6 still exists. We'll deal with that in a future video. But if I walk along the list now, I start at the head pointer, 10, 17, and I'm done. It doesn't matter that the list still sort of has the node 6 tangled up in it. If I walk from start to finish, I don't see the 6. That means the 6 isn't in the sequence, which means it isn't in the list. So what modification do I have to do to achieve that? Now, in future videos, we'll see that we don't have these node 1, node 2, node 3 names. And so we'll have to think of a different way of getting to these nodes. But for now, let's just make the modification just to get used to the splicing that we have to do. Let's use the node names. So I want to make node2.next, the next pointer of the node containing the 10. I want that to point to node 3, which is the node containing the 17. And actually, I think that's all I have to do. And there it is. I've removed the 6 from the list. So what we have done is actually constructed a linked list out of individual variables that we've created in main. We created a type to represent our node, and maybe you can verify to yourself, because of the way structures work, our elements don't have to be ints. They could be floats, they could be strings, they could be instances of a different structure. It isn't hard to do that because all we're doing is declaring an element of some type here. We've created our type, we've created 3 node variables, and then we've used this head pointer and a series of other pointers to interconnect them. We can then iterate over them using a loop. We can access elements using the arrow operator on the head pointer. Notice that except for that modification I made at the end, all of the code that I wrote was working with the list using only the head pointer and temporary variables. It never needed to know things like which element is stored in the node called node 2. That was irrelevant. All we care about the list elements is what order do I see them if I iterate over the list. So there is one problem with this, a really big one, which is what I want is the ability to make a list that's as long as I need. I want to do something like, I don't know, read numbers from the user and store them all in a list. But the way I've constructed this list, where I've used variables to represent each node, makes that sort of impossible. Because if I don't know in advance how many nodes I'm going to need, how will I make enough variables for them? It's almost the same problem that arrays have. Because I have to declare the nodes one by one, I can't make it so that I can just create new nodes on the fly if I use this representation. So the thing we have to pick up, the one remaining piece of the puzzle we have to solve is, what do I do if I want to create a node object spontaneously in the middle of my program? Maybe that's something you can think of between videos. If only there were a feature of the language that let me allocate storage suddenly at a moment's notice that I can manage myself.